All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. We were in the middle of some examples last time, so let's just actually get back to those. Also, the plan was to finish grading your test today before class, but that didn't work out. So I hope to finish at some point later today, at which point I will send you guys a mass email, let you know that it's been graded. You will be able to go into GradeScope. You'll be able to view your test. You will be able to see the grading rubric. You'll be able to see what you lost points for or gained points for. And if there's any issues or anything like that, you'll be able to use a feature called regrade request, which if you look at the bottom right corner of the screen, there's going to be like in the green ribbon, there's going to be a button called regrade request. So if you see that, oh, you didn't do something wrong, or you think I made a mistake, you can click that button and you can send off a sentence to me and say, hey, I think I deserve like 2 more points here because of blah, 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 right? So all that can be done and settled. And maybe I should see the syllabus here. Oh, by the way, I did send out a mass email yesterday about the final exam schedule. It's finally been posted. So you guys should know the dates of all your finals at this point, as well as, let me double check something while I'm here. There's, oh, never mind. I thought I had put the date in here. Let me go to like the main academic calendar. And we are in March. Okay, so yeah. Yeah, I just wanted to make sure, wanted to know how far we were from the last day you're able to withdraw from the class. So we're quite a ways off, it looks like. So April 28th is that day. For some reason I thought it was closer. Okay, so never mind. So you do have some time. And as I've mentioned before, I would definitely not make such a decision before seeing your first test grade and seeing me put in all your homework and everything to get a full picture of where you are, because you might not be where you think you are. So definitely I would not make any big decisions, any rash decisions at this point. I don't anticipate anyone failing this class. So worst case scenario, you get a D, and that's still passing. And for a lot of you, I would think that's actually okay. I mean, I know your GPA might suffer and you might not want it, but in the grand scheme of things, it's actually not that bad for a calculus class. I know a lot of you are biology majors, probably interested in pre-med and things of that sort, which is very common. And yeah, as far as I know, like a lot of people who got into med school suck at math. Their math grades aren't the best. It's not, I don't think in general it's going to really matter. It might matter for other reasons, like maybe if you want to go to grad school, you want to apply to a PhD program after you graduate, maybe trying to get some nicer grades would be nice. Yeah, I really don't think this class is a big of a deal. I don't think any of you should drop, but of course, if you want that option, it's April 28th. It's also, April 28th is also the last day to designate a course pass-fail. So maybe you might just want to say, I passed the class, but you don't want to grade, you don't want it to affect your GPA. April 28th is also the last day that you will be able to do that. As for the actual mechanism for how to do this, where to go and what to click and do all that stuff, like I don't really know. If you're interested, you should talk to an advisor or something, an academic advisor. I'm not used to that side of the Fordham system. Okay, so that's just some public service announcements. Let's actually get back to the matter at hand. Last time we were doing implicit differentiation. We basically understand that intuitively what we do is you just differentiate as usual, but whenever you differentiate a dependent variable, you multiply by the prime. That's pretty much it. So if you only have the variables x and y, x is your independent variable, then differentiate as usual, obey all derivative rules, product rule, quotient rule, chain rule, all of that's still a thing. But the difference is whenever we differentiate a y term, we multiply by y prime. At the end of the day, we have to solve for y prime. So we did a couple of that. We did something that did not involve x and y specifically, but the idea was exactly the same. Here our variables were v and p, and this was actually a bona fide true equation. This is from chemistry, van der Waals equation for a specific gas. We wanted to find out how fast the volume is changing as the pressure is changing, and we can do that by implicit differentiation. And that was just an example to show you that we're not writing functions in a complicated way just for the sake of math class. Sometimes in real life, the relationship you discover is discovered in a complicated way, if that makes any sense. It's discovered in an implicit way, but you still want to be able to analyze something based on calculus, based on rates of change, based on how much space something takes up. So we can't, so we need implicit differentiation. We also saw, if not last time, the time before last time, that there were times when we literally could not differentiate the other way around, right? Like without implicit differentiation, we were stuck. Like we were in a situation where it was actually impossible to solve for y. Not hard, literally impossible to solve for y. You can prove mathematically that it was impossible to solve for y in that situation, but we still could find the derivative. We still could find the tangent line. We still could talk about calculus type stuff, which is very useful. Then to motivate the next section, we looked at the derivative of x to the x. We looked at the fact that applying the power rule or the exponential rule that we had before would be incorrect because it does not fit the template. And we figured out what the derivative of that was by a process called logarithmic differentiation. That can be described in a process. So it's not like a new rule. It's more like a method or a process for finding derivatives of things that are particularly iffy to deal with computationally. So you have y equals f of x or some function of x. You can log both sides. Using the law of logs, you can simplify the right side. This will also make the thing that you want to differentiate easier to differentiate because logs will turn powers into products. It'll turn products into sums. It'll turn divisions into subtractions, etc. Logs have a lot of nice simplification properties. So you'll be able to simplify things and then differentiate implicitly and then solve for your y prime that way. And this puts you in a nice position in many cases. Some specific cases are if powers are a problem, right? If your power is complicated, if you have both a variable in your base and your power is when you would want to use a technique like this. And I'm going to show you a similar technique today. And sometimes if something is just hella complicated and you don't want to have to use the product or quotient rule on it because it's going to be a nightmare, logarithmic differentiation is also an option there. We did one such example. Example A here, the cube root of x to the 7, e to the 3x all over x plus 1 to the 4th. Like to do that directly, you need the chain rule because there's the cube root on the outer function. Then you have to multiply the derivative of the inside, which is going to take the quotient rule with the product rule built in, with the chain rule on top of that to differentiate the x plus 1 to the 4th and the e to the 3x. It was too cumbersome. So what we do is we hit it with a logarithm. The log allowed us to simplify the right side, in which case doing all those derivatives were trivially easy. And then we just solve for y prime by multiplying both sides by y. We get the derivative here. So that with that, we're all caught up. So we had one more example that I asked you guys to do. So that was the example we did last time. Now we want to do this one. So how do we do this one? What did you guys do?
wasn't sure if it was right, but I set it equal to y and then
Okay.
put ln on both sides.
So set y equals e to the x squared plus x to the x squared, and then?
Ln both sides.
So what does that look like over here? So you did something like this? Okay, so no, can't do that. What is the problem? Why can't I do that? What were you assuming here? Because remember here, what was going on? When you log both sides, right? So you have y equals e to the x squared plus x to the x squared, right? Now, what you should recognize is that this is, well, the left side, and this whole thing here is the right side, right? Which means to log both sides, it means you have ln of y, the whole right side, and then you have ln of e to the x squared plus x to the x squared. And that is not equal to ln of e to the x squared plus ln of x to the x squared, because logs don't distribute across sums. So you have to be very careful here. Logging both sides does not mean log each individual term on both sides, because that would actually be incorrect. That is assuming that the log distributes across the sum. So that won't work. So remember, I should probably state that warning. Logging both sides does not mean logging each individual term on both sides, because logs do not distribute across sums. So that was a very common mistake. So I just want to make sure that you guys don't know you can't do that. Do not distribute across sums. So that's a common mistake, and it's you don't want to do it. It does not work because of the log property. Okay, so maybe another try. So knowing that you can't do that, what would you try now?
Can you scroll back up so that I'll be able to see the problem again? I'm sorry.
Want to do that?
Thank you.
Ideas now. Here's a better idea. And I'll give you guys even a better idea, at least in my opinion, something that's even a better idea later on. So a better idea is to split the function. Okay, so here if I have y equals e to the x squared plus x to the x squared, think of this function as two separate functions. Think of this as, you know, some f of x and this as some g of x, right? Because we know that derivative distribute across sums. So clearly y prime is going to be the same as f prime of x plus g prime of x, right? Now, for f equals e to the x squared, we have a rule for that. It's actually pretty easy to differentiate that by itself, right? We have f prime is equal to 2xe to the x squared, right? Because the derivative of e to the u is u prime over u. So individually, I can differentiate that first term by itself. Now, I look at the other guy. Now, for g, this is the x to the x squared. Now, this is the guy that I don't have a rule for. This is the guy that's complicated. This is actually the guy that I need the log differentiation for, right? Notice that in the first term here, the e to the x squared, that's not particularly complicated. I don't need a log for that. There's no reason to put a log on that guy. I have a rule that to do that. So what I can do is I just think of these two things as separately. And I know we can do that because that's a property of derivatives. Derivatives distribute across sums. So the derivative of sum is just a sum of the derivatives. I know how to differentiate the first thing, so just go off to the side and do that. Then now we can focus on the second thing, isolating it. At this point, it's totally okay to log both sides because there's literally one thing on both sides. So I have ln of g equals ln of x to the x squared. That allows me to bring this x squared down. And so now I can differentiate both sides. Derivative of ln g is g prime over g. Derivative of this guy is going to be the product rule. So that's going to be 2x ln x plus x squared times 1 over x. So this is going to be 2x ln x plus x. Or I guess you could write it as x times 2 ln x plus 1, if you fancy. And so now my g prime would be, well, my g, which is x to the x squared, times all of that, x 2 ln x plus 1. I can clean this up a little bit. X to the x squared times x, that's just x to the x squared plus 1 times 2 ln x plus 1. That's not our final answer. So this means that if y equals e to the x squared plus x to the x squared, then my y prime is going to be 2x e to the x squared plus x to the x squared plus 1, 2 ln x plus 1. Via log differentiation only on the second term. I didn't need it for the first term, but I could just separate this. Okay. Now, pressing the button. Now, admittedly, this this might seem a little bit cumbersome that I have to break it into two things. And, at least, back when I was taking calculus, that's how I felt about it. Like, what? It's just more writing. I don't want to write anymore. Right. So there is another option where you can kind of do things on the spot, and you never have to like separate things and just go to the side and do this part and then go to another side and do this part. You can kind of do it all in one shot. So I'll talk about that and alternatives. To log differentiation. And this actually, again, comes from a rule that we know. This comes from a rule we know. Right? So the idea is, the rule is the following. If we have something, I don't remember what symbol I used last time. If this thing is greater than 0, then that thing is equal to e to the ln of that thing, right? Remember, we had that rule that says a to the log to the base a of x is just x. Equivalently, you can know that e to the ln of something is just the thing, right? Once it's valid to put that thing in a log, right? So at any given time, if you're looking at something positive, you could rewrite it as an exponential at any point. It's always true. It's always the same. These two things are equal, right? They just are. So let's use this rule to compute A. Let's go back to this guy, x to the x, and B, the guy we just did. E to the x squared plus x to the x squared. Okay, now we did both of these with log differentiation, where we followed that process. Set y equals to this thing, log both sides, simplify the right side, solve for y prime. But with this rule, you'll notice that I'm going to be able to do this like on the spot because I'm literally rewriting something in place, right? Like I don't have to go separate, like set y equals this, log both sides. But like I don't need to do that. I can just rewrite whatever thing I'm looking at. So here, how would that look like here? And you can compare this to the previous methods that I've shown you, and you can decide on your own which one you want. Like I'm not going to force you to use one versus the other, but if you need log differentiation, then there are two kind of varieties in which you can do it. So here, if you ask me d dx of x to the x, right? I don't need to go and set y equal to that. I just realize, oh, this is actually the same as you asking me e to the ln of x to the x. And so now what happens is that in the power, now I get the log and the power, can apply log rule in the power, which means this guy simplifies to e to the x ln x, because I can move that x down. And now that differentiating e to something is something that we know, right? So now using the derivative of e to the u is u prime e to the u. Well, this is just going to be the derivative of the power times the original function. What is the derivative of the power? Well, you'd use the product rule. This is going to be ln x plus x times 1 over x. Right? It's going to be 1 times ln x plus x times 1 over x. And I can clean this up a little bit. Ln x plus 1. And what is the original function? Well, it's just x to the x, but I rewrote it. And so that's the answer. You'll realize that that was the answer we got last time. What about the example we just did? Well, if you ask me to differentiate that, I don't need to separate this and set f equals this and g equals that, or set y equals this and figure it out. I can rewrite this on the spot. So the first thing is I'm not going to rewrite the e to the x squared because why would I? Like I know how to deal with that. However, the x to the x squared, I would rewrite that as e to the ln of x to the x squared. So over here, I rewrite. Now, I would simplify using the log rules. So this is e to the x squared ln x. Simplify by log rules. And now I just, I again use the rules. Use d dx of e to something is u prime times the original function. So for the first term, d dx is going to be, well, 2x e to the x squared. Plus, this one is going to be something times the original function. What is that something? Well, product rule. 2x ln x plus x squared times 1 over x. Cleaning this up a bit, this is 2x e to the x squared plus 2x ln x plus x, and this guy here is your x to the x squared. Right? So that's the derivative. And I could simplify this if I wanted to a little bit, like depending on what options you had. There was a common x here that I could factor out. And then the x to the 1 times the x to the x squared gives us that the x to the x squared plus 1, which we know was the answer from last time. Right? So I didn't have to separate anything. I could just rewrite something on the spot, right? Just write the thing as e to the ln of the thing. This allows me to get an ln of the thing, but it's in the power of an exponential. For calculus, though, this is not a big deal because differentiating e to something is easy, right? It's a very easy rule. And so once I get the ln to simplify the power, I can just apply my derivative rule to get to the answer. Notice that I didn't have to separate things. I didn't have to set anything equal to something else and log both sides. But it's just another option, right? And in some sense, it's safer. Like if you think of doing things this way and rewriting in place, you probably will never actually fall into this mistake accidentally. You're not going to like distribute a log across a sum by accident, because you wouldn't log both sides. You would actually just rewrite in place, right? So you can kind of avoid a little mistake. So in my opinion, this is like log differentiation, which it is because you're introducing a logarithm. But so it's like log differentiation, but better than log differentiation. It's like a party, but it's better than a party, right? So this is another option, right? And this is my preferred option for doing something that would require log differentiation, but it doesn't have to be yours. You can do it the way that I showed you last class in the beginning of this class if you want. But I find that this way is just, it's easier, it's nicer, it's cleaner, it's more compact. So just an option. Okay, let's see, where do we want to go from here? Ooh, fun. All right, we have like 60 minutes of fun left. All right, so now I want to actually segue into fix the scale here. Yeah, so now I actually want to segue into a new topic. New topic. And we're going to go back to everyone's favorite topic, limits. We now have enough knowledge for another special special technique. Called Lopez Rule. You have to say it with a French accent. Or yeah, it doesn't work as well. So it's l'hôpital, which is French for hospital. So, you know, a couple of years ago, I had a class where, you know, I told them that, and how they decided to talk about this rule is like they took the limit to the hospital. So I asked them, okay, so how are we going to do this limit? Take it to the hospital. And then I know that they're talking about Lopez Rule, because it's French for hospital. It's the hospital rule, but it was a guy's name. So it's Lopez Rule. Okay, so what is Lopez Rule? How it works? When does it work? Remember, special techniques sometimes are very context dependent. In math, everything is context dependent. Let's be real. So let's actually talk about that. So we'll need to discuss something that's called an indeterminate form. Now, when someone says indeterminate form, they really mean an indeterminate limit form, but we usually don't say the word limit. But it's very important that you understand that it's a limit form. It's not really a sort of evaluation of a function, as some people might think. So there's something called an indeterminate form. These are limit forms, i.e. forms that limit expression will approach that cannot be evaluated at face value, as there are competing, that's probably the way I want to put it, ideas. There is a short list of these guys, relatively short list. There are like 7 of them. So the indeterminate forms are and I always I recognize it when I see them, but I always forget one of them or something whenever I'm trying to list them off the top of my head. You know it when you see it with some experience, but sometimes I forget. So I wrote it down to make sure I remember. But I can talk about some obvious ones. For example, infinity to the 0 is such a form. So you're taking a limit of something to a power. What happens if the power goes to 0, but the base goes to infinity, right? There are competing ideas here, because on one hand, if the base is infinity, you would think the answer should be infinity. While on the other hand, if the power is 0, shouldn't the answer be 1, right? So it's like you have 2 different ideas for what the answer should be, and it's not exactly clear at face value which one would win. Is it infinity? Is it 1? Is it something else? Limits can be very strange, right? Maybe it doesn't even exist, right? So that's one of the forms. Another one is like 1 to the infinity is another indeterminate form, right? Because on one hand, if the base is 1, the answer should be 1, right? But on the other hand, if the power is infinity and the thing is like a positive number, like shouldn't it go off to infinity? Like, you know? So that's another one. Infinity minus infinity is another one, which some people find strange, but this is something that I brought up in my other class when we were discussing set theory. It turns out that there are different sizes to infinity. That's not always the case in the calculus context. Sometimes the infinities that we're dealing with are of the same size, but one function gets to infinity a lot quicker than the other function, because one function might be an exponential while the other is a polynomial. So while they're both going off to infinity, the exponential function is going to get to infinity a lot faster. And by comparison, the other infinity is going to be like 0, right? So there are times when infinity minus infinity doesn't make any sense. Is it 0? Is it infinity? Is it negative infinity? Is it something else? It's hard to tell at face value. Another indeterminate form is 0 times infinity. Because again, a competing idea, 0 times anything should be 0. But then we have this idea that infinity times anything should kind of be infinity, right? Should be infinite, like plus or minus, right? It's like, is it 0? Is it infinity? Like how, what, I don't know, right? 0 to the 0 is also 1. Again, base is 0. You would think the answer should be 0, but then a power 0, you should think the answer is 1. Like, which is it, right? It's hard to tell. There are some other ones like infinity divided by infinity, right? So again, for like I mentioned, some infinities can be bigger than others, or they can get to infinite values faster than others. And so the top might outweigh the bottom might outweigh the top. They might not outweigh either one. Maybe they move at the same pace. Like it's hard to tell what that is. Is that 1? Is that infinity? Is it 0? Is it something else? It's hard to tell. 0 to 0 is another one for obvious reasons. Like division by 0 isn't a thing. And if the numerator is 0, you feel like the answer should be 0. But if the denominator is 0, it's like illegal. Like if I write down division by 0, Jhevon's going to kill me, right? He's going to deduct all the points. So these are the indeterminate forms. So, 1, 2, 3, 4, 5. These are the indeterminate forms, like I'm introducing a band. My band is called the indeterminate forms. Yeah, 6, 7. Okay, so these are all indeterminate forms. We cannot determine them at face value. Now, here's the thing. L'Hopital's rule, the guy that I'm trying to introduce to you, does not apply. It applies to indeterminate forms, but it does not apply to all indeterminate forms. These two, right? And of course, this could be plus or minus. But these two, L'Hopital's rule, only, emphasis on only applies to these two. Now, in hindsight, if you go back to the test and you look at, it wasn't on a test, it was a quiz. It was a quiz, one of the previous quizzes. I forgot which quiz. Either the last quiz or the second to last quiz. I had a bunch of memes on that quiz about how, students try to use L'Hopital's rule on everything. So now you kind of get where that's coming from. L'Hopital's rule only applies in 2 very specific situations. But on the other hand, L'Hopital's rule is so cool that you feel like you want to apply it all the time. I've seen students apply L'Hopital's rule in situations where you're not supposed to apply L'Hopital's rule. They just love applying L'Hopital's rule. It's a really cool rule. And so there's this joke about once students learn L'Hopital's rule that they literally try to do every limit they encounter with L'Hopital's rule, which you should not and you cannot, right? L'Hopital's rule applies to these 2 specific indeterminate forms. Now, there is hope because of algebra if one of the other forms occur. We can often rewrite. Them to look like forms 6 and 7. Or something else. useful. Okay, so Lopez Rule only applies to these two situations. If you encounter any of the other 5 situations, most of the time you can actually rewrite it using algebra in a different way. You can probably rewrite it in one of the ways that Lopez Rule applies and then apply Lopez Rule. But you might be able to rewrite it in just another way where the answer becomes obvious. You no longer have any competing ideas, right? So, how many exams can I get to? Let's actually cut the suspense and tell you what Lopez Rule is. Lopez Rule. Oh, and this just reminds me. I haven't uploaded the video for last class yet. And that's because last time, remember, I had technical difficulties. I got dropped from the internet. And so there's a bunch of dead air in the video. And there are some other spots where when I logged back in, it wasn't working properly, like it removed the spotlight. And so a couple of students were caught on camera, which I don't want. I want to protect their privacy. I don't know if you guys mind, but in general, I don't want that. So I have to edit the video by snipping out the dead air as well as blurring the camera whenever one of you are caught on video. So that's just going to take time. I just haven't had the time to do that yet. So that's what's going on there. Yeah, Lopez Rule. Okay, suppose we have the limit as x approaches a of f of x divided by g of x. So you have a limit of a division, right? One function divided by another. And that f over g gets closer to 0 over 0 as x gets close to a, or f over g approaches infinity over infinity as x gets close to come on. As x gets close to a, plus or minus, right? So you have a limit of a division, and you know that, oh, both the numerator and denominator get close to 0 as my x gets close to a, or both the denominator and the numerator become infinite as x gets close to a. Like either the top one is plus or minus infinity, and at the same time, the bottom one is plus or minus infinity. So the denominator and the numerator are doing the same thing. They're either both approaching 0 or they're both approaching infinity. In other words, they're getting closer to one of these two limit forms. Then here's what Lopez Rule says. Then, then the limit as x approaches a of f of x over g of x will be equal to the limit as x approaches a of f prime of x divided by g prime of x. You can literally differentiate the top and the bottom and take that limit, and you would actually get the answer for the original limit, provided both limits exist. I do also want you to note this can be used repeatedly, right? So you have a limit. It's a limit of a division, right? You realize it's going to 0 over 0 or infinity over infinity. What you can do is you can hit it with Lopez Rule. You differentiate the top, you differentiate the bottom. Again, we're not doing the quotient rule. We're literally just differentiating the top, differentiating the bottom. You differentiate the top, you differentiate the bottom. This might make the function simpler, right? Because you know that derivatives can break down powers and all sorts of stuff. And if you find the limit of that new guy, it's actually going to be the same as the limit of the original. Now, it turns out sometimes you can take a derivative on the top, a derivative on the bottom, and you still get something that's indeterminate. You can actually do it again. You can actually do the second derivative and the second derivative and the third derivative and the third derivative and the fourth derivative and the fourth derivative. You can keep just taking derivatives on the top and bottom until you get something nice. I would recommend though, but simplify after each application to make sure that you needed to do it again. Okay. So what I'm going to do is I'm going to write down 6 examples that I want to go through. We're obviously not going to do all of those now because we're pretty much out of time. I might just do a couple, but the couple are they're super obvious. So it's what we knew how to do it before this, but I just want to show you that Lopez Rule will give us the same answer that our intuition told us that it would give. So the examples are, it's not 6, it's 7, but we'll do maybe the first 2. The limit as x approaches infinity of e to the x over x. Limit as x approaches infinity of ln x over x. The limit as x approaches 0 plus of x ln x. The limit as x approaches 0 plus of x raised to the x. The limit as x approaches infinity of 1 plus 1 over x to the x. The limit as x approaches infinity of e to the x minus x. And finally, the limit as x approaches 1 from the right of 1 over ln x minus 1 over x minus 1. Right? So these are the guys we are going to finish up next time. And then we're going to move on to another topic, which was another bonus topic on the exam, linear approximation, as well as some marginal analysis. But these are the guys. Let me quickly do the first 2. Limit as x approaches infinity of e to the x over x. Quickly, what is the answer?
E to the x.
Come again? The limit. As I approach it, what is the answer? Like the final answer. Tell me the final answer. Because it's something you should actually know by looking at it.
Should be infinity.
It should be infinity. Why? Like if you had to show your work, what would you write?
Honestly, I believe that they both go to infinity, so it's going to be infinity over infinity.
Yeah, but we didn't know how to deal with that situation until like just a few minutes ago. Like prior to this class, how would you have done this?
I would have done what you showed us.
Which is?
Which would be the, if I believe I'm saying right, the d. D over dx. Bracket. So yeah, the limit to infinity equals d over dx.
No, why would you do that? Like before today, we've never done limits with derivatives, like ever. Like taking a limit and finding a derivative are very different things. But before today, what you would have done is just say, this is top heavy, right? Remember, I gave you a limit strategy that says determine it based on the behavior of the function. We know that exponentials grow faster than polynomials. The top is going to overwhelm the bottom. The bottom is very small compared to the numerator, and so it should go to infinity, right? And you would literally say top heavy. No derivatives involved. However, here, so we know the answer, but I do want to show you that you would get the same answer. Here, applying the Lopez rule, we would do the following. I would say this is equal to, so first of all, I would notice to apply Lopez, first, note that this guy actually approaches infinity over infinity. As x is approaching infinity, e to the x approaches infinity. And as x is approaching infinity, x approaches infinity. So this is approaching infinity over infinity. So this means L'Hopital's rule is an option. Which means I am going to go through, and how I want you to show it is that you can just write an L apostrophe H on top of that equal sign. This indicates you're applying L'Hopital's rule. Right? So L'Hopital's rule would say, differentiate the top, derivative of e to the x is e to the x. Differentiate the bottom, derivative of x is 1. So now this is just like the limit of e to the x as x approaches infinity. Well, yeah, that's infinity. Makes a lot of sense, right? Now, for something like this, I wouldn't use L'Hopital's because it is literally something that you should be able to look at and in a few seconds know the answer because exponentials grow faster than polynomials. Similarly here, what is the answer?
Infinity?
Infinity?
No, 0.
It's 0, right? Because this one is bottom heavy. Right? There's a log on top and a polynomial on bottom. Polynomials grow faster than logarithms, so I know it's going to be 0. What would L'Hopital's rule say? But what I can just notice here is note, if I take the limit as x approaches infinity of ln x over x, this approaches infinity over infinity. So L'Hopital's applies. You don't have to write out what I'm writing out in red, but I'm just indicating that since we're doing this for the first time. ln increases like that, right? So as you're going up to infinity, the output becomes infinite. X increases like straight up like that. So as you're going up, the outputs are infinite. So what would you do here is say, okay, I'm going to apply L'Hopital's rule, which tells me that I can differentiate the top divided by the derivative of the bottom. So this becomes the limit as x approaches infinity of now 1 over x. And what is that? Well, it's 0 now in a very obvious way. But again, this is kind of something that I would say should be obvious without anything like L'Hopital's rule, because you should know how different functions relate to each other, how fast they grow in relation to each other. So yeah, so those would be how you apply L'Hopital's rule. Now, go and try that. So here you'll notice that this becomes 0 times infinity, right? Technically 0 times negative infinity, right? Which is an indeterminate form, but it is not a L'Hopital's rule indeterminate form. So you now have to figure out, how can I rewrite this to maybe use L'Hopital's rule, maybe use something else, and get to the answer? What is that limit, right? And you want to do the rest of these. So we are going to, we're going to stop there. We're going to wrap up there. We'll finish these examples up next time, as well as start a new topic. Will we finish that topic? We can probably finish that topic next class too. Okay, all right. So that is it. Hopefully that was clear. Thank you for your time and attention. I have a good weekend. Like I said, at some point today, I mean, I have a few like office hours and stuff, but I know there are meetings. So I expect to finish grading today, like worst case scenario, like tomorrow morning or something like that. But whenever the grading's done, I'll send you guys an email and send you guys instructions for how to like look over your tests and if you have any issues, what to do. That being said, thank you for your time and attention. I will see you guys in the next one. Ciao.